Okay, so we are done with organic chemistry, right? So congratulations to everyone. And today we are coming back to the chapter I skipped in the beginning. That's chapter 4 of the syllabus and the text, which is, there was a time I used to pronounce this as stoichiometry, but that's not how it's pronounced. So for a proper pronunciation, actually going to ask Merriam-Webster how it's said, and this is how it's supposed to be pronounced.
Stoichiometry.
Stoichiometry.
Hmm.
Right? So stoichiometry it is.
Yes.
And this is basically a chapter about calculations, right? With regard to, so WRT is with regard to, how much of a chemical, and I say chemical, so it could be an element, it could be, right, a compound, molecule, ion, whatever, right? How much of a chemical is present or takes part in a reaction. And so there's some concepts we're going to cover and then use those concepts to do calculations. The very first concept that we're getting into is something that we've come across in an earlier chapter, I believe in chapter 2, atoms, elements, and compounds, or it was chapter 3, either of those two, and that is relative atomic mass. Do you remember this? Relative
Yeah.
atomic mass, right? Given as AR. Well, the R needs to be smaller, subscript. Otherwise, if you write AR, it's going to look like argon, which is an element. That's not what we're writing. So relative atomic mass. So to recap, the definition of relative atomic mass is the average mass of the isotopes of an element compared to 1/12 of the mass of a carbon 12 atom. Now, obviously, scientists had uses a benchmark, but we know that carbon 12, the mass of a carbon 12 atom is 12 units, atomic mass units, not 12 grams, but 12 atomic mass units. And so, what's 1/12 of 12? Hmm? Guys, you there?
Yes.
What is 1/12 of 12? Seriously.
Can I answer?
Yes, you can.
Uh, it's one.
Yes. But I was actually, holding my breath like, oh my god, please don't give an incorrect answer. Right? So that basically tells us, if you take a look at the periodic table, whatever mass is given for each element, that is actually right in comparison to a carbon atom, and so that is the mass you use. So right, we have hydrogen, which has a mass of 1 unit, right? And then you've got magnesium, which has 24, calcium, which has 40, sodium, which has 23, right? And obviously all the other elements. Iron, if I fit that in over here, has 56. Right, chlorine has 17. So whatever, elements you remember. And so these are the masses of these different elements. Okay.
Yep.
Now, uh, what we say is, so now when we are, we're carrying out experiments, right? On paper, we can show something like, carbon, where's the whiteboard? C plus O2 giving me CO2, right? But obviously these guys that are reacting in the product that's being formed have mass. And so the mass of carbon is 12, as we know. And for oxygen, right, a single molecule of oxygen is 16, and sorry, atom of oxygen is 16, and so you got two of those in the oxygen molecule, right? And then over here you're getting, obviously, right, 12 plus 16 into 2, which is giving you how much now? Right, 44. So this is 12, this is 32, and this is 44. And so all of these, we're not putting a unit against them. I said atomic mass unit for, because that's a reference, but we're not saying grams or something, right? Why? Because this is relative atomic mass, right? So it's relative, which means we're not
Yeah.
putting a unit to it. But what we can do is, because when we are weighing these out, when we are handling oxygen, or when we are handling carbon, or when we have carbon dioxide in a tube, or whatever uh, equipment we have and it's being produced, it obviously exists physically, and something that's physical has actual mass, right? And we know that actual mass is measured in grams, right?
Yeah.
So what we can do is, we can say, okay, carbon and oxygen giving me CO2, and so this is 12 grams of carbon, and this is 32 grams of oxygen, giving me 44 grams of uh, carbon dioxide.
Yeah.
Seems okay?
Yep.
We converted. Haram, you following? Is she there?
Yes, sir. She's there.
Yes.
Okay. Now, this seems easy enough, right? But there's a question. When you talk about atomic mass units, and atomic mass units are like really small. So I think they've mentioned something in the text about how small it is. Yeah. So what they mention is, right, as an example, if I just sneak it in over here in yellow. So they mention that for a single atom of sulfur, a single atom of sulfur, what is the mass? Like how much does it actually weigh? Actual mass. And so the figure they give is 0 point, right? 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, 05316, 05316 grams. How small is that?
Almost that it doesn't exist.
An individual atom, yes, right? So can you convert this to standard form, Sophia?
Me?
Yes.
I mean, I can try.
Do it, please.
Okay, wait. You need a standard form, right?
Yeah.
Okay. Mm. Can I have a little help here, though?
Well, you're moving the decimal place to the right. And so this is right, and you want it to come up till here.
So 5.3?
Let's keep the number as it is, right? So 5.316. Because
Oh,
in terms of significant figures, this is 4 significant figures.
yeah.
So
Okay.
let's keep it like that.
Okay.
Right? So 5.316, we could do, 553.16 or 531.6 or 5316 as a whole, but let's do 5.316 times 10 to the power, and since you're moving it from left to right, you're going to have a power negative,
Yeah.
and so that's 3, 6, 9, 12, 15, 18, 21, 22, and 23. So the mass of a single sulfur atom is 5.316 into 10 to the power minus 23 grams, which if you expand it is this, which is, as you said, right? I mean, for a single atom, you would say it
It's
is,
barely there.
yeah, it's negligible, it's beyond negligible, right? I mean, it's like nothing,
Yeah.
but it's not nothing, obviously. So why highlight this? When I simply went ahead and converted, oh, carbon has 12 atomic mass units, its relative atomic mass is 12, and I simply went ahead and said, oh, so if a single atom of sulfur has that low, like that small a mass, is a single atom of, because this is like right, elemental carbon, right?
Yeah.
And we're talking about a single atom of carbon over here, not like a lump of carbon, obviously.
Yeah. Yeah.
So is a single atom of carbon going to have a mass of 12 grams? Does that make sense to you?
No.
No, right? Is a single molecule of oxygen going to weigh 32 grams?
No.
Right? Obviously, a single molecule of carbon dioxide is not going to, because if that were true, then, right, if oxygen weighed 32 grams per molecule of oxygen, then, the air around us would be super heavy.
Yeah.
Super heavy. I mean, it is heavy. We learned from physics that, you know, it's the atmospheric pressure is about, like, the weight of the air around us is about 500 newtons, which is about 50 kilograms of air around us, but our body is tuned to that, so we don't really feel it.
Yeah.
But that's on a side note, right? Even if we like convert, like we calculate, okay, fine, so how many atoms, like we can do that. 50 kilograms is how many grams, right? 1 kilogram is 1,000 grams, so that's 50,000.
Yeah. 15,000.
50,000 divided by 32, which gives me only 1,562.5 molecules of oxygen, which is obviously not true.
Yeah.
There are not only 1,500 or 1,600 molecules of oxygen in the air around me, right? So this doesn't make sense, does it?
Yeah.
So then the question is, what, like, how does the mass that we're using over here relate to the number of molecules of oxygen in that mass? right? So mass versus number of, let's say, particles. Why I'm not saying molecules, because over here we've got atoms. This is a molecule. This is also a molecule. We could be talking about ions. So let's just say particles, right? For a general term.
Like
So,
we multiply the number of molecules to the molecular atomic mass.
but how would you know how many particles there are?
Like it's written over here, like
Huh?
there are two molecules of oxygen
There's one molecule
or
of
two atoms
oxygen.
of
There's one molecule of oxygen. Again, the question is, does one molecule of oxygen weigh 32 grams? Does that make sense when we just saw that one atom of sulfur has that low, like minus 10 to the power minus 23 grams, 5.3? If it's that small for sulfur, how can oxygen weigh so much? It doesn't make sense. Right? It doesn't fit. And from this we come into, like, there was a chemist by the name of uh, Amidio Avogadro, if I'm pronouncing that correctly. Just a sec. So, Avogadro's law. Yeah, Amidio Avogadro. So, there was an Italian scientist by the name of Amidio Avogadro, and what he noticed is that take when taking the relative atomic mass of a substance, like in this case an element, because atomic mass is for elements. So let's say element in grams. So that's what we did, right? So relative atomic mass in grams, what you get is a particular number of atoms, right?
Yeah.
It always contains a particular number of atoms. And what is that number? That number is 6.02 into 10 to the power 23. So what this means is that we said we had 12 grams of carbon. That's what we said over here, right?
Yeah.
And so what that means is that in 12 grams of carbon, there are 6.02 into 10 to the power 23 atoms of carbon. Okay. We had 32 grams of oxygen, and this is a molecule. And so in 32 grams of oxygen, we have 6.02 into 10 to the power 23 molecules of oxygen, right? For carbon, which is 44 grams, sorry, carbon dioxide. So if you have 44 grams of carbon dioxide, what you have is 6.02 into 10 to the power 23 molecules of carbon dioxide. And so what he discovered through his observations and experiments, that again, when taking the relative atomic mass, so 12 atomic mass units of carbon, you convert that into, so right, one carbon atom is 12 atomic mass units. So if you take 12 grams of carbon, if you convert that relative atomic mass into actual mass in grams, and so whatever substance you're taking, like you're taking water, let's take water, right? How many molecules of water are there, right? So let's, what is the relative molecular mass? So in case of molecules, right, if you recall, relative atomic mass is for elements, single like atoms, and for molecules it is relative molecular mass, right? So it's actually 44 grams is the relative molecular mass for carbon dioxide, right? So what's the relative molecular mass for hydrogen? Do you remember the numbers?
Sir, could you repeat that?
Which part?
The question?
What is the relative molecular mass of water?
18 gram?
Yes, right? So hydrogen is 1 and you've got 2 of these guys, and oxygen is 16, and so you get 18. And so when you're taking 18 grams of water, which is something we can very easily measure out, right? Because in terms of pure water, 1 gram is 1 ml, right?
Yeah.
So you can take 18 mLs, and in that, right, because 18 corresponds to the 18 grams of water corresponds to the relative molecular mass of water. How many particles, like how many molecules of water are you going to have in there? You are going to have 6.02 into 10 to the power 23 molecules of water. Does this make sense now?
Yes.
Right? Now, to put things into perspective, let's find the mass of a single atom of carbon, just like we did for sulfur, right? So to find the mass of a single, right, atom of carbon, when 12 grams has 6.02 into 10 to the power 23, one carbon atom is 12 divided by 6.02 into 10 to the power 23. Would that be correct? Is that how you do it?
I would guess probably not.
Not?
No, wait. Oh, yeah. Okay. Okay.
Right? And so what's the answer we're getting, Sobhi?
May I calculate?
Yes.
We are getting. Wait, just a minute. Give me a minute. That's multiplied. 6.02 is multiplied by what?
10 to the power 23.
Uh, I I'm finding it hard to calculate it by 10 to the power 23.
Okay, so the response I'm getting is 1 point,
9 something.
yes, and so that's correct. Why are you finding it hard? Right?
Well,
We could round this off to 2. Technically, it depends, right? So we could say it's 2, but 1.99 into 10 to the power minus 23 grams. And if we look at this value, and we look at the value for an atom of sulfur, and if we take a look at the periodic table, let me just refer to the periodic table, right? And we know that sulfur is element number 16 and has a relative atomic mass of 32, whereas carbon is element number 6 and has a relative atomic mass of 12. Okay,
yeah.
so if we compare those, we saw, we'd expect, obviously, because sulfur has a relative atomic mass of 32, we'd expect a single atom of sulfur to weigh more than a single atom of carbon, right? So sulfur is heavier than carbon, isn't it?
Yes.
Right? And so given that scale, 5.316 into 10 to the minus 23 for a single atom of sulfur, and compare that to 1.99 into 10 to the power minus 23 for a single minus 23 grams for a single atom of carbon. Does now that makes sense, doesn't it?
Yeah.
Yes, Haram? Is it making sense to you?
Yes.
Okay. So 1.99 into 10 to the power minus 23 grams, the mass for a single carbon atom, that makes sense. But again, the thing is that if you're carrying out a reaction which looks like this on paper, a single atom of carbon and a single molecule of oxygen giving you a single molecule of carbon dioxide, you can't do that in the lab, can you? You can't pick out a single carbon atom, or can you?
Yeah.
You can't, right? So this is impossible, quite simply, right? Picking one single out for an experiment. And so what you're doing is you are weighing out in grams the relative atomic mass, right? And so you're like, okay, how much have I taken? Well, you've taken 12 grams. Okay, fine, but how many particles do I have? Like, right? And this concept comes in handy later on. So, right, for each atom or molecule, right, whatever we're dealing with, it will have this many molecules when we take its relative atomic mass or its relative molecular mass. In fact, let me go to the next page, right? So for molecules, in fact, for atoms, right, its relative atomic mass. For molecules, its relative molecular mass. So this is written as AR, and this is written as MR. And right, if the molecule happens to be ionic, right, for that it's called relative formula mass. It's just a different name, it's the same thing.
Yes. Okay.
Okay. And so when you take these relative masses and put them into actual grams, you get 6.02 into 10 to the power 23 particles. And this number is called Avogadro's number or Avogadro's constant. Obviously named after the scientist who figured this out, Amedeo Avogadro.
Yeah. Okay.
Okay. And this many number of particles is called 1 mole of a substance. Okay.
Yes.
1 mole, right? So how much is 1 mole of NaCl? You take the, right, this is an iron, so you take the relative atomic mass of each. So
It's 58.
Na is 23, Cl is 17, and so you do the math and you get NaCl is 48 actually. No, sorry,
58?
50.
Okay.
Right, so sodium, oh yeah, sodium is 23 and chlorine, oh my, chlorine is 30.
Isn't chlorine 35?
Okay, so, well, it is 35, but we are looking at a single molecule.
Okay.
So that would be 17.5. And so NaCl, just a sec. Just a sec. I might be confusing myself. Yeah, okay. So my bad. Right? 35 is for a single atom of chlorine. I was looking at it as diatomic, right? So that would be Cl2, which would be 70 actually, right? So yeah, 23 and 35. So Sobia, you were correct, and that gives us 58. And again, taking those as actual grams, and so because it's ionic, the relative formula mass of NaCl is 58 grams, and so 1 mole of sodium chloride is
58 grams.
58 grams, right? You want to do something a bit, I mean, I wouldn't say challenging, but still, you want to try something else?
Wasn't this challenging?
Oh no.
Oh my god. Okay.
What is 1 mole of, let's say, calcium carbonate? Right, and
Uh,
so the relative atomic mass for calcium is 40.
and for carbon, I mean, it's 12.
Yes.
So,
And for oxygen it is 16.
for,
6 mole
isn't,
multiplied
isn't
by
oxygen
3.
3?
Well, yes, you multiply by that by 3 because there's 3 oxygens. So you
So
do,
that would give us 48.
yes. And so you have 40 plus 12 plus
40.
48, which would give us how much now?
100.
100?
100. And so, right, the relative molecular mass of calcium carbonate, or in fact, right, calcium is an ion and carbonate is an ion. So formula mass, I guess. So CaCO3 is 100 grams. And so 1 mole of calcium carbonate contains how many grams?
100
100.
grams.
Or you could say
But
it the other way around, 100 grams of calcium carbonate is 1 mole.
And if we do it in Avogadro's number, whatever that's pronounced, it's,
Avogadro,
yeah. So it's 6.022,
not 22, 6.02.
not 22.
Why would it be 22?
Oh, okay, okay.
like
And
it won't be the same.
Huh?
Like it won't be the same. No?
Yeah, so the number of particles, that's the interesting thing. 58 grams of sodium chloride have
yeah,
the Avogadro number of particles, which is 6.02 into 10 to the power 23 particles. Again, you see, I'm not putting a unit over here because we're talking about number of particles. And 100 grams of calcium carbonate have 6 point. So these are like molecules, right? This is an ionic compound. It is a molecule, however, right? So 6.02 in 10 to the power 23 molecules of sodium chloride in 58 grams. And similarly for calcium carbonate, because the stuff that we're dealing with is heavier. Calcium is heavier, oxygen is heavy, right? And more so because you got three of those guys, right? And so obviously it weighs more. Weigh not in the physics sense, but in the layman sense, so there's more mass, right? So 6.02 into 10 to the power 23 molecules of calcium carbonate in 100 grams of calcium carbonate. So that's the interesting thing about Avogadro's number. If you take the relative atomic mass or the relative molecular mass or formula mass of an element or a compound, right? And you convert that to grams, you will have that same number of particles every time.
Okay.
Make sense? Is it making sense now?
Yes.
Good. Because this tends to be, tricky, and students find it really confusing.
But like, carbon would be 6.02 multiplied by 10 exponential to 3. Like 1 mole of carbon would be.
1 mole of carbon. What about one
Yeah.
mole of carbon?
Like it would be 6.02 multiplied by 10 exponential to 3.
Hmm. Individually, yes.
Uh, okay.
If you're talking about just 1 mole of carbon,
Yeah.
right, which would be 12 grams, and that would have 6.02 into 10 to the power 23.
Okay. Like a whole compound won't be like 6.0
It will.
multiplied.
It depends. So, I mean, obviously, calcium carbonate is a compound, is it not?
Is it? It is
Right? Sodium chloride is a compound, is it not?
compound.
And so,
Yes.
Yeah.
right, when you talk about 6.02 into 10 to the power 23, when you talk about carbon, so carbon is an element. So we're talking in terms of atoms. So 12 grams of carbon, elemental carbon, will have 6.02 into 10 to the power 23 atoms of carbon. Whereas for sodium chloride, 58 grams of sodium chloride will have 6.02 into 10 to the power 23 molecules of NaCl. Right? So this guy, the Na and the Cl, right, the ionic bonding and stuff, they're these many of these guys in 58 grams,
Okay.
right?
It will remain the same for all the compounds and atoms.
Yeah, so for when talk about calcium carbonate, right, there are 6.02 into 10 to the power 23 molecules of calcium carbonate in 100 in 1 mole. Now how much what's the mass of 1 mole depends on the different elements that are present in that substance. So it could be
Okay.
58, it could be 100. If we go back, it could be 44, it could be 18. It depends on what we're talking about. So the mass can be different, but if you've got 1 mole, it's going to have that many number of particles in it. Okay, clear?
Okay. Yes.
So what I'll do is I'm going to clear this out. Okay, and I'll stop here and let you digest that. And so the next time we come in, we are going to take this forward and we're going to talk about how we can use this information in the chemical reactions that we do.
And also, can we do much more questions in the next class?
You mean calculation?
Yeah.
Well, this chapter is all about calculation, so we will come across those. Yes, right. There is the
Okay.
concept. So right now, what I did is I introduced the concept of the mole to you and reasoned it out how it makes sense. Okay.
Yeah.
So for example, Haram, right? Let's calculate the mass of one molecule of sodium chloride, right? So let's do 58 divided by 6.02 into 10 to the power 23, right? What is the mass of one molecule of sodium chloride?
1 molar.
One molecule of sodium chloride, not mole, right? So we
Okay.
can do 58,
Yeah.
oh, not 85, 58. right? And that gives us 9.63 into 10 to the power minus 23 grams, which makes sense, right? Now, obviously, it's heavier than sulfur, which also makes sense because sulfur is atomic, as heavy as it is, but NaCl weighs more than sulfur, right? And so one molecule of sodium chloride weighs 9.63 in, right, one molecule. Now, they're not going to ask you the mass of one molecule, right? But this, I'm just doing this to put things into perspective for you, right? That individually molecules weigh very, very, very less. And so obviously you're not dealing with individual molecules, you're dealing with lumps of things, you're dealing with actual measurable masses that you can work with. And so when you're doing that, right, you have all those many more particles, right? So
Yeah.
what is the mass of one molecule of calcium carbonate? So that's 100 divided by 6.02 into 10 to the power 23. And so this is going to come up to, right, 1.66 into 10 to the power minus 22 grams. So it's much heavier. You can see that it actually, right, went up from minus 23 to minus 22.
Wouldn't it be 166 point 112?
Why?
You multiply by 10, right?
Why multiply by 10? I'm dividing 100 by this value, right?
Yeah.
So this is what I'm getting.
Oh, okay.
I mean, you've got the numbers right, but I think you're placing the decimal wrong.
Yeah. Okay.
Okay. Right, so that is the mass of one molecule of calcium carbonate. Now, just to leave you with something interesting, I guess, if you want to find the number of molecules in let's say 25 grams of calcium carbonate, right, how would you do that?
Hmm.
Right,
Right.
I'm not going into it right now, but this is the kind of stuff that we can do. So we can find the number of, right, we can find the number of molecules in a particular mass of a substance, knowing how much one mole is in mass, right, and how many particles there are, and obviously that's the Avogadro number. We can also find the number of moles in a measured mass of substance, right? So
100 gram?
for example, you have 250 grams of sodium chloride. So how many moles is that? Right?
100?
What?
Wait. You're talking about the number of moles, right?
Yes. So
The
these,
related
huh? I'm not
the
asking you.
related
I'm not asking you to calculate it right now. I'm just telling you. Next time
oh,
we're going to get into these type of calculations and
Ah,
more.
okay.
Okay. So this is sort of a prelude to next class.
Oh, okay.
All right. So I leave you with that, and I'll
Okay.
right. Hopefully the concept, the basic concept of Avogadro's number and the mole is clear, and
Yeah.
right, you'll be
yeah.
processing it and read through the book and stuff on your own. And the next time we'll make progress, and I believe it should take about 2 maybe 3 classes to get through this chapter, right? And then we'll only have the last chapter left, and we should be able to get it done with by end of Feb, hopefully, inshallah.
Inshallah. Okay then. Allah
Okay.
Hafiz.
Yeah.
Yeah.
Allah.